तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, last class we were discussing the circuit where the inverter circuit with a bipolar transistor, and as I said, it is very important to understand the working of this circuit, because this forms the basis of almost all bipolar logic circuits. So, we shall just do a brief recapitulation. So, what we had done is we have seen that if you have a circuit like this, with a bipolar transistor and base resistance, collector resistance and a supply voltage, and the input voltage here and the output voltage given at the collector. Now, for this circuit, how to analyze? You have to draw the load line. So, you take the output characteristics of the transistor and then you draw the load line, and you know how to draw the load line. So, this is going to be a straight line, and the points of intersection with the axis is given by VCC on the VCE axis and VCC by RC on the current axis. Now, for this, so this is for different values of base current, all right. So, we had seen that now when V in, so if you plot the output voltage versus the input voltage, when the input voltage is low, okay, the base current is almost 0. So, the output voltage, okay, is given by VCC, and once it starts conducting, okay, then what happens is as you go on increasing the base current, the collector current increases, with the result the output voltage drops. Okay. So, the point of intersection is given by the operating point is given by the points of intersection of this output characteristics and the load line. So, VCE drops, output voltage drops till finally it comes to this point, okay, where afterwards if you go on increasing the base current, the collector current is almost a constant, and so we say that the collector current has saturated. Okay. So, this is once it reaches this point, okay, this value is called VCE sat, okay, and this is the saturation current. So, what happens is if you plot the corresponding input output characteristics, you get something like this. Okay. All right. So, this is the plot which we have seen. So, this is the characteristics of an inverter. So, when the input voltage is low, the output voltage is high, and when the output voltage is high, when the input voltage is high, the output voltage is low. So, this is the characteristics of an inverter. So, this is already something which we have already done. Okay. Now, let us discuss it slightly more quantitatively. So, when the transistor has gone to saturation, the collector current is given by IC sat, okay, which is equal to VCC minus the collector emitter drop VCE sat divided by the collector resistance. Okay. So, and now we also know that when the transistor is in the active region, the collector current is related to the base current by a factor beta f, okay, forward beta of the transistor. But once it goes to saturation, then the ratio of the collector current to the base current becomes less than beta f. Okay. All right. So, we can say that for the transistor to go to saturation, okay, IB, okay, all right, must be greater than IC sat by beta f, okay, for the transistor to go to saturation, okay, which means that IB must be greater than VCC minus VCE sat by all right. Okay. So, now we can actually put some values, okay, and see. For example, let us suppose for this circuit VCC is equal to say 3 volts, okay, say RC is equal to say 1 kilo ohm. Let us put RB equal to say 0.5 kilo ohm, all right, and say beta f is equal to 50, all right. Now, in addition, let us see, we have already seen that some conditions we have already discussed last class, that for example, just for the sake of analysis, let us assume that when the transistor is cut off, okay, VBE is less than equal to 0.6 volts. In the active region, VBE lies between 0.6 and 0.7 volts, and for the transistor to be saturation in the saturation region, VBE is equal to 0.7 volts. And also let us assume that VCE sat is equal to 0.2 volts. Okay. Now, with this data we can actually find out the different points in this characteristic. Okay. Now, so when V in is 0 volts, okay, what is the value of V out? V in is 0 means IB is 0, and so IC is also 0. So, V output is equal to VCC. So, this voltage here in this characteristics, this is going to be equal to 3 volts, okay, that is equal to VCC. Now, the next point is at what is the value of input, okay, at which this output starts to fall, okay, this value, that is when the transistor is in cut off, the output is equal to VCC, and when the transistor starts conducting, okay, all right, the output is going to fall. So, that voltage is equal to 0.6 volts. Okay. After 0.6 volts, when V in exceeds 0.6 volts, then there is going to be a base current and a corresponding collector current, with the result output is going to fall. So, from 0.6 to 0.7 volts, the transistor is in the active region and it behaves as an amplifier, okay, and you know that this amplifier has a negative gain. So, you know that a sort of common emitter amplifier. So, the output is going to fall as the input increases. Okay. So, now the next thing is this point, all right. At this point, so here the transistor has gone to saturation. So, once it goes to saturation, what is the output voltage equal to? 0.2 volts, all right. And what is the input voltage, okay, at which the transistor has gone to saturation? How do you calculate that? You have to know first what is the base current, okay, at which the transistor goes to saturation, all right. What is the base current? How do you calculate? You can calculate from the relation given here, okay, that IB must be equal to VCC minus VCE sat by beta f RC, okay. So, that is the relation. Now, we know all these values, okay. So, we can plug in these values and find out the base current at which the transistor goes to saturation. So, what it is, what is it? 3 minus 0.2 divided by 50 into 1 k, okay. So, if you do that, I think it will come to it should come to 56 microamperes, okay. And so, that is the base current when the transistor has gone to saturation. So, now we have to find out the input voltage at which this goes to 0.2 volts. That is very easy, because this voltage we know is 0.7 volts when the transistor has gone to saturation, plus IB into RB, okay, that is 56 microamperes into 0.5 kilo ohms, okay, that will give you the drop here. So, that is the input voltage when the transistor goes to saturation. Okay. So, this value if you do it, okay, I think it works out to 0.728 volts. Okay. So, this actually gives us the total characteristics. So, that is how you can do it quantitatively, all right. So, finally, we see that if the input voltage is low, that is below 0.6 volts, okay, output voltage would be is equal to 3 volts, and when the input voltage exceeds 0.728 volts in this case, okay, that is the input is high, the output voltage is going to be low, which is 0.2 volts in this case. Okay. So, this is the inverter characteristics, all right. So, for this inverter circuit, when the input voltage is low, the output is high, and the output voltage is, when the input voltage is high, the output is low. So, that is one aspect of an inverter. Okay. So, if you have an input waveform, okay, that is it is an input waveform like this, all right. What do you expect? When the input is low, the output is high, output is when the input is high, the output is low. You expect something like this, okay, all right. So, it is an inverted waveform. So, that is what is important, okay, for us in digital circuits. But actually, okay, there is another aspect to this. So, one is of course that this you should get something like this in a digital circuit, but the another important aspect is when this input changes from low to high, okay, how much time does it take for the output to react, okay, that is to change from high to low, okay, that is going to be a small displacement, okay. So, that is the delay, okay. So, that is also a very important aspect of the circuit, and one must really design in such a way that this delay is going to be minimum, okay. The other delay is when the input goes from high to low, the output changes from low to high, and so you have something like this, okay, okay, and these delays, okay, okay, need not be the same, okay. So, we shall now take up this aspect, okay, the same inverter circuit, okay, from another consideration, that is the switching consideration, okay, that is how much time does it take, okay, from the switching point of view to react when the input changes, okay. So, okay. So, for that, let us assume initially that for the same circuit which we have drawn, okay, I am just going to draw it again, okay, it is the same inverter circuit. It is very important to understand this, okay. So, suppose the input goes from low to high, okay, suppose this was low, it went to high, okay. This low means the transistor was in cutoff, okay, there was no base current, suddenly it has gone to this value where the input voltage is Vf, all right. Then what happens? What is going to be the base current? There is going to be a base current, isn't it, all right. This base current is going to be equal to V in minus whatever is the VBE divided by RB, okay. So, I can write IB is equal to V in minus VBE by RB, okay. And you know, in a forward bias, this base emitter junction is obviously going to be forward biased, and this VBE is usually, you know, in this type of circuit where you have a limiting resistance, this voltage maximum it can be 0.7 or maybe slightly higher, all right. And if V in or this Vf basically at this point in time when you consider this input is gone high to Vf, okay, Vf is much greater than VBE, we can say okay, all right, you can say IB is nearly equal to Vf by RB if Vf, all right, when Vf is very much greater than. So, you all have an almost constant in base current. Okay. Now, the next thing to see is what happens when you have a constant base current flowing. Initially, there is a sequence of events which takes place actually. Okay. Now, if you look at the base of the transistor, okay, when this base voltage was low, the input voltage was low, the transistor was cut off. What was the charge stored in the base? Okay, there was no excess base stored charge. Okay. Now, as the base current flows in, a constant base current is flowing in, okay, what is happening? The base charge begins to build up. Okay. All right. So, the relation again is so now for that, okay, let us consider a transistor. Okay. Okay, let us go back a little bit. We have already discussed the transistor, the base current of a transistor. It consists of, in the forward conduction mode, okay, of a transistor, it consists of basically two components, if you remember. What are those two components? One is the injection of carriers from the base to the emitter, and the other is the recombination of charges in the base. Okay. Now, if the doping concentration ratio bit of the emitter and the base is very large, that is, the emitter doping concentration is very much larger than the base doping concentration, we can for all practical purposes neglect the current component, that is the injection of carriers from the base to the emitter. Okay, and we can say that the base current is almost totally made up of the recombination in the base. All right. So, let us take a transistor where the emitter doping concentration is very much greater than the base doping concentration, and the base current is totally composed of the recombination in the base. For that type of transistor, okay, we can write this relation that the base current is equal to QB by, this is for an NPN transistor, okay, tau n plus this relation we have already seen for when we discussed the diode. So, basically if you understood a diode, is very easy to understand the operation of a transistor. Okay. So, the base current is equal to, so this is the recombination in the base, okay, and that is proportional to, that is the base charge divided by excess base charge divided by lifetime. So, that is going to be the recombination part. And so, if the base current is more than this, what happens? The base charge is going to build up. Okay. There is charges flowing in. So, it partly compensates for recombination, and whatever is excess, it increases the stored charge in the base. So, as the stored charge is increased, this QB term goes up. So, the recombination goes up, the rate of increase of charge goes down. Okay. So, finally, what is going to happen, because it is building up, the rate is going down, but the amount of charge is building up, finally this goes to 0, okay, IB becomes equal to QB by tau n, you reach a steady state. Okay. So, basically at when for that particular amount of base current, you will reach a steady state where IB is equal to QB by tau n. But you understand right now that it is going to take some time. Okay. It is a not an instantaneous process, it takes some time. So, what we are interested in is how much time. So, basically you have to solve this differential equation, okay, for the QB. All right. So, if you solve this equation, you will get, I am just solving, I am just writing the result. Okay. You can very well solve it yourself. Okay. You take the initial condition that QB is equal to 0, okay, you will get QBT IB tau n 1 minus e to the power minus t. Tau n is of course lifetime, the minority carrier lifetime in the base, okay, that is the electron lifetime. Okay. So, this you see that when t is equal to 0, QBT is 0, QBT reaches IB tau n only after an infinitely long time. Okay. All right. So, that is, you can see, visualize it from this equation itself. All right. So, that is the relation. Now, the question is, we have put this equation. So, basically what is going to happen is the total base charge is going to increase. Okay. Now, I will just draw this figure. Okay. This is the base, say, of a transistor, NPN transistor. Okay. Now, the initial charge was 0. Okay. So, the charge is building up. Okay. So, the charge profile, is going to be something like this. With time, it goes on like this. It sort of, okay. So, with time, right, increasing time. Okay, this is the emitter side, that is the collector side, obviously. All right. So, the charge builds up like this. This is a charge profile, minority carrier charge profile in the base. Okay. So, as with time it goes on increasing like this. All right. So, you see that with time it is increasing. What is happening to the collector current as the base current is with time? Collector current is increasing. For example, here you see it was initially it is 0, then it went to here. So, the collector current depends on the slope of this profile. Okay. So, that keeps on increasing, and as the collector current keeps on increasing, what happens to VCE? It goes on decreasing. Okay. All right, is not it? And so, it goes on increasing, VCE goes on decreasing. When VCE becomes equal to VBE, what is the condition of VBC? That is, the collector emitter voltage is the same as the base emitter voltage. Base collector drop is 0. Now, if the collector current keeps on increasing even further, what happens to VBC? VCE will become less than VBE. Okay, that is, the collector voltage will be less than the base voltage. What does it imply? That the base collector junction has become forward bias. That means that the transistor goes to saturation. So, you see that it goes up like this, all right, and this it will go on increasing, you see, until the total charge stored here, okay, becomes equal to IB tau n. Finally, it will go up IB tau n. Okay. The charge will keep on building up, although the transistor has reached saturation. Okay. It will not stop till you have reached IB tau n. Okay. Okay. Now, so what is going to happen is, so what we have to know is what time. So, basically the idea is when you apply an input voltage, if you look at this figure here, you have applied an input voltage here. Okay. Now, what you want to do is, as the input voltage goes high, the transistor, you want to drive the transistor to saturation. Okay. So, what is the time taken for the transistor to reach saturation? Okay. That is, when the input goes high, we have seen an inverter, the output goes to 0.2 volts. Okay. That is when the transistor has reached saturation. So, what is the time required for that? How do you do that? In this equation, we have to see when does, at what time t, okay, that is QBT equation, at what time t, okay, QBT becomes equal to the value at saturation. Okay. What is this value at saturation? How much QBT? What is the value of QBT at saturation? Yeah, that is, it is going to be equal to the collector current at saturation. Okay. We have already seen what is the value IC sat. Okay. IC sat into the forward transit time. we have already seen the forward transit time of a definition of the forward transit time of a transistor. Okay, it is the ratio of the base charge to collector current, isn't it? That is the definition of forward transit time. All right. So, we can write it in terms of the forward transit time. So, at saturation, if you go back to this equation now, QBT is equal to IB tau n 1 minus E minus T tau n. So, you have to write at T is equal to say T on, that is the time required when the transistor goes to saturation. Okay. At T is equal to T on, QBT is equal to IC sat into tau T. Okay. So, I will write in this equation, all right, when T is equal to T on, that is the T on is the time required for the transistor to go to saturation after you have applied a step. Okay. QBT into tau, I will write tau T, which is the transit time, which actually is the forward transit time of a transistor. All right. So, tau T is the transit time. Okay. So, in that equation we have to substitute, all right, this expression. Okay. So, once you do that, okay, you get the value of T on. There is another important relation we have to use. Okay. I hope you know this relation. The beta of the transistor, forward beta of the transistor can be related to the lifetime in the base and the transit time. Okay. Because the collector current is equal to it is, see, the base current is equal to QB by tau n, all right, and what is the collector current equal to QB by tau T, isn't it? QB is equal to IC into tau T. Okay. So, collector current is a QB by tau T. So, we can write beta f is equal to tau n by tau T. Okay. Because I will just write, since IC is equal to okay. So, from this relation you get tau n by tau T. So, now if you substitute this, all right, in this equation, all right, and you take this relation, okay, you will get that T on, I will just write down the equation for T on, you can very well do the calculations. I think I do not need to do that. Tau n ln I think I called it IF. IF is of course the forward base current, okay, all right, the base current. I am writing it IF because later on we will see a reverse base current also, okay. So, that is why I am writing here IF. IF is actually the base current, okay, that is flowing in, okay, all right. Okay. Now, you can see we have seen the condition for saturation. What is the condition for saturation? That beta times IB must be greater than IC sat. Okay. Sorry, this is actually IC sat. All right. Okay. So, of course, if beta IF is equal to IC sat, it is never going to saturate, the transistor is never going to saturate, all right. You can look at this. Okay. If if beta IF is greater than IC sat, okay, this becomes a fraction and it is going to saturate. Now, if just let us take a small example. Suppose let us say beta f IF is equal to twice IC set. Okay. What is T on equal to? So, this becomes half. Okay. So, it becomes tau n ln 2. Okay. Now, if beta f IF is equal to say 5 times IC set, what is T on equal to? So, this becomes 1/5. Okay. So, this becomes ln 1.25. Okay. So, what do we see here? That if IF, beta f is a constant for that device, okay, for the transistor. Now, if IF is, IC sat also is a constant, you must remember, for a particular circuit, all right. That depends on the collector resistance also, collector resistance and the supply voltage and all that. So, now if for a given circuit, if you increase IF, okay, what happens? That is the base current. If you increase the forward base current, what happens is the time required for the transistor to saturate goes down. Okay, it reaches saturation faster. It is quite obvious because you are pushing in charge at a higher rate. The increased base current means what? The rate of flow of charge, current is rate of flow of charge, higher rate of flow of charge. So, the current builds up, the charge builds up faster, you reach saturation faster. Is it clear? So, to have a fast switch on, okay, you must have a large base current. Okay. It is not only sufficient to have beta f IF greater than IC sat to reach saturation, but the more the base current, the faster is the switching on time. Another thing one must remember is that all this is proportional to tau n, which is the lifetime. So, if you want to have faster switching on, tau n must be made, lifetime must be made small. Okay. But that is also has a certain disadvantage because the beta of the transistor is tau n by tau t. So, if you make tau n small, beta reduces. Okay. So, tau n must be made small, at the same time tau t also should be made very small, that is the transit time, okay, the base transit time should be made also made very smaller. How can you make the base transit time smaller? By reducing the base width, correct. So, I mean that is a design of a good switching transistor. Okay. You must make tau n small, but at the same time you should make tau t also much smaller, that is you must have as small base width as possible. All right. So, this is the switching on transient. Okay. Now, we have to look at the other case, okay, that is from this you apply voltage now, okay, from Vf, say I should say this is 0, say let this be Vr, okay, that is a reverse voltage is applied, okay, a negative voltage is applied. Okay. Now, what is going to happen once a negative voltage is applied? The same way, if you look at again, we have to use again this same relation. Okay. This is the fundamental relation. Okay. All right. So, the base current now becomes, see, another thing you must again what we have discussed in the case of diode, okay, the base emitter voltage cannot change instantaneously. Okay. You have a lot of base charge. Okay. Now, according to this relation, the base charge is going to reduce now because this has become negative. Okay. dq dt becomes negative also, but it will take some time. Okay. So, again if you go back to this figure here, okay, which gives the charge profile. The charge profile which had built up, okay, is going to again go down, okay, and as it is going down, see it is going to go down, okay, the base emitter voltage is going to reduce, okay, but it will take some time, okay. So again see for a long time, okay, this base emitter voltage, okay, that is the voltage at this junction, okay, is going to be positive unless the charge goes down to 0, all right. So basically what is going to happen is the charge is going down to 0, okay, and then at this end it will again go down to, it will become negative, okay. So for all this time, when until you have removed all this charge, the base emitter voltage is going to be positive, all right, okay, and then it starts going negative, okay. So now with increasing time, all right, I think the direction of the arrow, is going to reverse it. So this is with increasing time, all right, this charge is going to reduce, okay. So what happens is, although you have applied a reverse voltage here, okay, at the input, okay, this voltage, okay, for a long time is going to be slightly positive, okay, going down, okay, towards 0. So what happens to, again if you go back to this relation now, IB is equal to V in minus VB by RB, okay. VB is again small compared to V in, now V in is negative, all right. Again what you have is IB is going to be, if you look at this relation, previous relation, instead of VF you are going to have VR, okay. So IB will be equal to VR by RB now, okay, the reverse voltage minus RB, that is IB is going to be negative. You are going to have a large negative current flowing out from the base, okay, all right. Reverse base current is going to flow in this direction, okay. Is it clear? Now what is that reverse base current doing? It is actually doing a very good thing, it is removing the excess stored charge, okay. So again if you want to find out how much time, now you have applied a negative voltage, so you want the transistor to go from saturation to cutoff, all right. So now I will just let us draw this another figure, I think I will draw it here. So initially, so when you applied a voltage, you see the input voltage going from negative to positive and then positive to negative, okay. This is the input voltage V in, all right. So this is VF, say this is the forward voltage and this is the reverse voltage VR, okay. Now what is, if you plot the charge, okay, QB, okay, what has happened is, if you at this point, okay, it went up exponentially, okay, all right, and this is value is IF tau n, where IF is the forward current, okay. Now it reached saturation sometime, see IF tau n is much greater than the charge required for saturation. So see, suppose if it reached saturation here at this point, that is this is equal to say IC sat tau t, okay. So here at this point it reached saturation, okay, but the charge goes up all the way here, okay. Now what happened is, so it is going to be something like this, okay. Now you apply a reverse base voltage, there is going to be a reverse base current, okay, and this charge is going to decay. Okay. So, it goes down like this. All right, you are pulling out charge, this charge is going to go decay, is going to decay. Now, up to this point, okay, from here to here, okay, that although you have applied a reverse voltage, the transistor will remain in saturation. Okay. So, here, okay, up to this point, because the charge is greater than that what is required for the transistor to be in saturation. Okay. So, up to this point the transistor remains in saturation, okay, and after that the current starts to fall, okay, and finally it is going to go to 0. Okay. So, if you now look at the collector current, okay, if I plot the collector current, okay, you will get it is going to go something like this up to this point. Okay, the transistor goes to saturation, all right, it is going to remain in saturation, okay, even here it remains in saturation, current has not fallen, okay, and then it is going to fall. Okay. Is it clear? Because only after this it is going to fall. This is the charge at saturation, all right. So, once the charge comes down to that, then only it is going to decay. So, this time, okay, for which the transistor remains in saturation, okay, even after you have applied a reverse voltage at the input, is called the storage delay time. Okay, it's got TSD is the symbol which is generally used. Okay. Okay. So, this is the storage delay time. Okay. It is very important. Here you have applied a reverse voltage, the collector current IC, okay, it will be like this, okay, it remains in saturation even after that is there, okay, and then it goes down. So, again how to calculate this TSD? Very simple, the same relation here, okay, we have to take this IB is equal to minus IBR, okay, and again what is IBR? You know that if the input voltage for all that time, okay, up when it is even when it is saturated or goes down to 0 current is slightly positive, okay. So, you can take it is almost equal to V in by RB, okay. So, that is minus IBR. So, minus IR you can say, or yeah. So, because forward current we have taken IF, so this is IR. So, the same relation you solve again, all right, and there is an initial condition, okay. You solve this same equation, okay, that is IB is equal to QB by tau n, and the initial condition is QB 0, okay, that is base charge at time 0 is equal to IB tau n, okay, all right. Now, if you solve this equation, you will get, again I am not solving this equation for you, you can very well do that, okay. You get tau n, just writing the result okay, IF IR e to the power minus t by tau n minus IR tau n. Okay. So, this is the relation. Okay. Now, how do you find out the storage delay time? At t is equal to TSD, QBT will be equal to, at t is equal to TSD, QBT will be equal to IC sat to tau t. Okay. All right. That is, you can see for yourself. All right. If you go back at this curve here, all right. At t is equal to TSD, this is we have made it at this is equal to 0. So, at t is equal to TSD, the charge will go down to IC sat into tau t. Okay. All right. So, if you solve this equation now, you will get TSD is equal to, I just again write down the relation, tau n ln C sat by beta f plus IR. This IR is of course these are the modulus values. Okay. So, I just this TSD, that is the storage delay time, is tau n, that is the lifetime, ln IR plus IF, IR the modulus, okay, the amount of reverse current, okay, we do not take the sign, IR plus IF divided by IC sat by beta f, okay, plus IR, all right. Okay. So, this is the relation for the storage delay time. Now, obviously, if IR becomes very large, okay, that is you can neglect IF with respect to IR and also IC sat by beta f with respect to IR, what is TSD equal to? It is equal to 0 because the ln 1 is 0. Okay. Obviously, if IR is very large, you are removing the charges faster, okay, and so the extreme case storage delay time is 0, I mean it becomes infinitely large. But normally, okay, you can also see that with if IR is larger, TSD will be less. Okay, if you go on increasing the reverse current, the storage delay time will be less because this fraction is going to reduce. What about with IF? How does it depend on IF? That is the forward current. If IF goes up, TSD goes up. Okay. Why? Because if IF was larger, okay, then QB 0, okay, this the initial condition, okay, okay, this is IF, sorry, QB 0 is IF into tau n, okay, that is the forward base current into tau n. So, the initial charge itself was larger, okay, if the forward base current was larger. So, to come down to IC sat by tau t, IC sat tau t, it is going to take more time. So, if you have larger forward current, okay, you are storing more excess charge in the base, okay. So, it will take more time to remove that charge, okay. So, the delay is going to be larger. So, basically you see, but you cannot reduce IF because if IF is small, the on time is going to be high. So, you actually require a large forward current, forward base current to switch on the transistor faster, and you require an even larger reverse current, okay, to switch off the transistor faster. Okay. IR must be greater than IF, okay, in order that TSD is small, storage delay time is small. Okay. Then of course, finally, so if we come back to this curve again, okay, so this is the storage delay time, and then there is another delay time before the transistor actually goes to cut off, okay, that is the what is called the discharge time. Okay. In order to calculate the discharge time, it's again very simple. You again take this relation here, QBT is this relation for QBT, and you take the value at discharge TD, okay, that is the total time required for the transistor to totally cut off, okay, QBT is equal to 0. Okay. You solve for that, okay, and that will give you the total discharge time. Okay. All right. I think I will take that up in the next class. Okay. So, that gives us a total picture of the different delays involved in switching the transistor on and off, and one must really appreciate this, and because if you want to compare between the different circuits, how fast is one circuit compared to the other, that gives that is mostly due to what are the different mechanisms for removing base charge or creating this base charge, okay, in a bipolar transistor. So, we shall take up again in the next class.